Right, let's talk about LSP optimization. So, there's a few considerations here with optimizing our LSPs. Let's have a talk about how all this works. First of all, optimization allows for LSP rerouting through CSPF computation. So, essentially, over time, in the topology, there'll be topology changes, there'll be new LSPs will be created, perhaps old ones will be removed over time. So essentially, if we disable optimization, which is disabled by default, the LSP's path just remains fixed until there is a manual topology change. So until you actually manually change that LSP, nothing's going to change. However, you can enable optimization, and the configuration is to set optimize timer, in which case you then put in place a time frame or a frequency actually in which optimization will occur. So how often will optimization occur? And you do that on a particular label switch path. So we can do it on as many label switch paths as you like. So what happens then is that the CSPF algorithm will take a look at the topology and it will evaluate a number of parameters. And if it finds a favorable situation, it can then re-signal that LSP through a better path. So what does it look at? It looks at the CSPF metric is not higher than what it currently is. The CSPF metric is equal. The path must have fewer hops. So these are the parameters, these are the constraints, these are the conditions under which optimization will occur. The new path does not cause preemption, does not worsen congestion overall, so it compares the available bandwidth on each link from the new and old paths, starting with the most congested links first, reduces congestion by 10% overall. So it will compare the aggregate available bandwidth on the new and old path. It does that for the least full tie-break rule. Intentionally conservative. So you don't want optimization to be occurring excessively. Optimize, there is an optimize aggressive option in which you can limit re-optimization to the IGP metric only, and that will result in more optimization or more rerouting. Adaptive mode is a option that you can set on an LSP, and that means that a new LSP will be signaled up before the old LSP is torn down. So if it says, if the optimization conditions are met, and the LSP in fact can be re-signaled for a better path, what will happen is the new one will be signaled up before the old one is taken down. We kind of want that to happen. So you have this make before break capability. So the new path comes up with the same session ID, different sender template, and with a different style of reservation. If you look at our reservation styles that we have been using so far, if you take a look at our RSVP, the style we've been using has been an FF style. This is a different style, it's an SE style. This is a shared style. So we're actually sharing what the result of that is that the path resources are shared by multiple paths. And essentially what that allows us to do is to avoid counting a path twice. So because in actual fact the path belongs to the same LSP, so one might be getting signaled up, the other one's going to be torn down, and it just avoids a double counting of the path during that process. You can also do that on primary and secondary paths. where a path has got an LSP as a primary path, has a secondary path, and this avoids counting the bandwidth on those paths twice. So the bandwidth, instead of being unavailable, is actually available for new LSPs to be signaled up. So we're using this SE reservation style. We can take a look at that in the labs. So when this is configured at the LSP level, the adapter prevents double counting of resources for the primary and secondary paths. This is an example of the configuration. So we edit protocols MPLS tables with the path. Under the path, we set adaptive parameter. So here's the two styles that we've got. So far, all our paths have been FF style. And if you actually take a look at the MPLS extensive, you'll see that that's the reservation style that we've been using. In this particular style, every session has got its own identity and every session's got its own bandwidth. So this is really good where you want to have multiple paths, each reserving their own bandwidth. You may want those paths because maybe you want to load balance those paths. They are completely separate paths and are related to each other, so they each need their own bandwidth. They're each actually using that bandwidth that's been assigned to them. Whereas the SE reservation style is each session has its own identity and the sessions share a single bandwidth reservation. So what's happening is that you've got multiple paths, but they really belong to the same LSP. And you're not actually sending traffic over the multiple paths simultaneously. But at the same time, you want the multiple paths to be up. But you don't want to count the bandwidth reservations on those paths twice. So in other words, if we are wanting to signal up another LSP, then we're saying that the bandwidth is available rather than allocated. So we're not counting it twice, we're only counting it once. That has benefits where we actually have got these primary and secondary paths that we've brought up. Okay, so we take a look at this this particular setup here. This particular configuration asks the question: will the secondary physical path green be up in an up state or a down state? Well, first of all, if you look at the configuration parameters under green, it's in the standby state. Okay, so what that means is that the path is actually signaled up, it's actually signaled up. Now, we've got a bandwidth requirement. We've got a bandwidth requirement of 85 megs. How do we got the 85 megs? That is the question. I don't see anything there that's telling you we don't. So we'd say that yes, it is in fact signaled up. It is in fact signaled up. So just on with our optimization, main points there is that we can set things up so that the system will automatically recalculate paths over time. We'll automatically re-optimize the paths that we've got so that within our MPLS structure, every now and then we can set a time. Maybe it'll happen every 12 hours, whatever time frame you might think is suitable, and how often things change around on your network. But every now and then, the CFPF algorithm will take a look at the paths that you have set to be re-optimized, and it will see if there may be a better path for those LSPs, and it will re-optimize them, build the new paths, and then tear down the old ones. Okay. We can also set the adaptive mode. on it, which prevents the bandwidth from being counted twice between primary and secondary paths, and that is very useful when we're not actually using the secondary path. We've just got it up, we've signaled it, but we're not actually passing any traffic across it. So it would be better if we didn't allocate that bandwidth, if that bandwidth was still available for other paths. But really, what we're really wanting to do with our secondary path is have it available in the event that our primary path fails. And only then will we actually use the bandwidth. Okay, so had a bit of a look at optimization. So just taking a look at what we covered in this chapter, we had a look at default traffic protection behavior of RSVP signal LSPs. And what we discovered is that it takes a very, very long time for, in the event of a failure, for first of all the failure to be signaled, and then for a new LSP to be signaled up. And just from our own experience in our lab, just waiting for a new LSP to come up will take a minute or two. And then you've got to add the time that it will take for the old LSP to be signaled that it's failed. So we're really looking at, could be looking at 4 or 5 minutes for this to happen. So we looked at how these primary and secondary paths can help with that by having a secondary path already signaled up, ready to go, which will reduce that down, but still not great. We're still got some problems with the time it takes to fail over the secondary path. Looked at how LSP priority and preemption operate. We discovered that if one LSP has got a higher setup priority, then other LSPs hold priority, and that new LSP requires bandwidth that is not already available. It can in fact tear down an existing LSP to set itself up. We also discovered that we can request for that new LSP to be rebuilt elsewhere before it gets torn down. We have a look at fast reroute. What we discovered is that fast reroute is specific to an LSP, and what it does is it allows all of those on the LSP to calculate a detour path around all of their downstream nodes, or not all of the downstream nodes, around the next downstream node, so that if the path to that node fails, that node itself fails, it will immediately have a detour around that node. What was the benefit of that? The detour can be activated in a fraction, a very small fraction of a second, rather than the default behavior which takes minutes to fail over to a new path. We looked at the configuration of link and node protection, and what we discovered is that that is focused on protecting a particular link between one router and the next, or protecting the path between a router and its downstream. So if it's downstream failed, it will actually have a whole bypass LSP that goes around the failed node or around the failed link for that matter. So what is the difference between this and fast reroute? Fast reroute is very specific, or is specific to a particular LSP, whereas link protection is specific to a particular link. And link protection and node protection can be used, the same link protection and node protection bypass LSPs can be used by multiple LSPs. So it can be used to protect multiple LSPs, whereas fast reroute protects a single LSP. And if you've got many LSPs that you need to protect, fast reroute is not very scalable, because each and every LSP has to calculate its own detour and maintain that state. So it's very resource intensive, whereas the link and node protection, the same bypass path is used by multiple LSPs, so far more scalable if you're wanting to protect many LSPs. We had a look at optimization options, and we discovered that we can set up our system to recalculate, using CSPF to recalculate paths for LSPs at various intervals to optimize the whole system overall. Alrighty, so what we're going to do after this next break is we're going to get stuck in and do some labs, and we'll actually do the labs for this, this section on optimization. not optimization, but on link protection and optimization. This is actually the last lesson before we go into our 2-week break. And when we come back from our break, we're going to start with VPNs. Okay, and the VPNs really takes the whole thing up to a whole new level, to be honest with you, because the VPNs are built on everything we've talked about so far. The VPNs are going to rely on all of this, and it takes up to a whole new level, and then we'll be building the VPNs on top of our MPLS infrastructure. And we get into a whole new lot of really interesting BGP routing stuff at this point. Okay, which is real interesting. So we're going to get into that when we come back from our break, which is a 2-week break, which starts next week. But the Savo, we will do the labs on this chapter. Okay, so we'll go to lunch and get into this when we come back.